Okay, CRC. CRC is short for cyclic redundancy check. Cyclic is the one that you keep checking. And it's actually, it's like a division operation, right? So, for example, you take your data, imagine your data is a number, you divide it by another number, and you get a remainder. We add to your number whatever complements that's needed to that divisible. What does that mean? I'll say it in mathematics. It's much easier. Okay, let's say this is your data, 37. That's the data you want to send. And you and I, we agree on a divisor. So we need a key or some code or something like that. But it's not a secret thing. Let's say 5. So as a sender, you divide your data, which is in this case 37. This is just to give you the idea of how CRC works. This is not exactly how it works, but almost. So 37 divided by 5, anybody knows what the result is? The result is 7, and the remainder is 2. Right? So 7 times 5 is 35, there's 2 remainder. So now, let's say, what would complement this 2? Like if we add you some more numbers to 37, how much do we need to add it to make it divide by 5 without a remainder? Now, 2 to 5, we need to complement that. What complements it is 3. So if we add 3 to this one, that will make it 40, right? 40 divided by 5 is 8, and remainder is 0, because 8 times 5 is 40. So you send your data 37, and you say the complement is 3. This is how CRC works. So it sends you your data unchanged, but at the end, it sticks a number that I had to add. So if you add this to that number and divide it by the agreed divisor, you will have a division without remainder. Okay, so this is exactly the idea. But we know division is so slow, so it couldn't be fast. Yeah, but we don't do division. We do XORing, because XORing is another logical operation that almost works like division. So this is how it works, and this you need to be able to do this. So for example, let's say here's the data that we want to send. Now I'm going to do 2 operations. Now you're a sender. The sender has to do something similar. So it's just like this one. The sender has to do the division and find out what the remainder and put the complement there and send it with the frame. The receiver now has to include that frame, that complement there, and do the division and check is the remainder 0 or not. Now, in order to do this, it involves 4 simple steps. 1, as a sender, just identify, just make sure you know where your data is. That's the data, that's clear. You get a frame or a packet or the whole packet, but we'll use short one. The generator, that's the divisor. We're going to divide this by a number. Let's take a number 5. So now we know that's the generator. It's called the generator. This is the one that will generate the remainder for us. Okay? And then, that's it. Second step is append zeros. In order for division to work, you need to add zeros to the end of the data. How many zeros? You see how many bits here, and add 1 less than the number of bits. So I'm just going to say 1 less than the length of the generator. So this is the generator. This is called the generator. It has 3, is the length of 3. the generator must have no zeros on the left. The generator, one of the conditions, the generator must start with 1 and ends with 1. It's just a condition. So we don't have, oh, I'm going to add a couple of zeros to the left, they mean nothing. No, they mean something. So don't have zeros on the left. This is the length of the generator. Usually the generator is given to you, all networks, almost all networks in the world, they use the same generator. There are scientists, mathematicians that looked at these generators and they said, okay, let's find out the best generator that can give the best possible results. And they found it, and they put it in a standard, international standard, and they call it CRC standard, and there it is. This is the best generator to use. So it's not a secret number, and if you are a programmer, you need to go and pick that number and use it in as a generator. Right, but it's not 101. It's you know, depending on how long you want it, there are different classes, but they're about 16 bits. You know, they're 2 bytes normally, the standard one, or 3. So now it says append zeros. So we need to append zeros. How many zeros do I append here? 2 zeros. Remember, they are not part of the data. And this is going to be the redundancy that we're going to send. So it's fairly short. At the end of the frame, this is added at the very end of the frame. The frame can be 3,000 bytes. So compare this. We'll be adding 2 bits to a frame or a packet, as opposed to the parity system that we add 1 in 8. Or if it's 7, we have to add 1. If it's 7 million, we have to add 1 million bits at the end, or bytes. This one, we add only few bits to the entire frame. So from redundancy, this is perfect. This is very good, the minimum. Right, and now start the division operation. So how do you start? You must start with the same number of bits. Can't start with smaller. So it's a long division. I don't know if any of you is familiar with long division. Don't worry if you're not. You don't have to worry about it. Normally we divide and put the number here, 1. We don't have to worry about it. In division in binary, it's either 1 or 0. So let's say it's 1. 1 multiplied by 101. You write 101. And normally we subtract. But this is where this happens. Don't subtract. It's XOR. I don't know if you are familiar with OR operations and XOR. That's called exclusive OR. If you forgot it, I'll remind you what OR or XOR. Now let's say it's OR. We do the OR. If we take 2 zeros, 0, 1, 1, 0, and 1, 1. These are the, you know, the possible bits here. ORing, that means if one of them, if A, let's say this is A and this is B. If A or B is 1, the result is 1. Here, none of them is 1, so the result is going to be 0. This one, B is 1, so the result is 1. A is 1, the result is 1. And this is both of them, either this or this, so the result is 1. But here's where the exclusive OR, XOR means not the 2 of them, only one of them. The word exclusive means only 1. You can't have 2 of them. So it's similar to OR except the last bit. You can't, if the 2 of them are 1s, no, we specifically want only exclusive, either A or B that needs to be 1, not either one of them. So this is the XOR table, just to remind you. So I look at it from a different way and say, okay, if both are 0, the result is 0. If both are 1s, the result is 0. So they're both the same, the 2 bits, the result is 0. If they're different, it's 1. It helps me go through this faster. So this is what you need to do. What's 1 exclusive with 1? Exclusive OR 1. The result is 0. They are the same. 1 and 0 is 1, and 0 and 1 is 1. Now, get rid of the zeros on the left. It's easier to get rid of. Now, and you must always have the same number of bits. So bring as many bits as you need to have 3 here. In this case, 3. If there are 5, then you need to bring a few more. So let's say we bring the next one down here and mark it with an arrow or something. So because sometimes you might bring the same bit twice, or you forget about a bit. So again, 3 divided by, well, 1, 1, 1 divided by 1, 0. It's always 1 at the top. You don't have to write it. We are not interested in it. All you have to do is bring down 1 times 101, you write 101 here. So all we've done is put 101 here, and we put it there, and we put it at the next step, and so on. Same thing. Now we divide again, or XOR. Don't forget, it's not a division, it's XOR. So this is the third step, divide. But just so to remind you, it's not division, it's XORing. So, all right, at the very end there, what's the result here? 1 XORed with 1.
0.
Oh yeah, I have a volunteer, thank you. And 1 0? Yeah, are you answering me? Go on. 1, yeah, and 1 and 1? Thank you. Woo. And what do I do next? Get rid of this one here, this 0, sorry. And what will I bring down? Only 1 bit, so that's 101. Now we have the same number of bits. Bring down the 101 again. Okay, next person. Just, yeah, elbow the guy next to you, yeah? What's the result? 0, 0, 0. Good. Get rid of all the zeros on the left, and we need to bring few bits. How many bits will I bring now? Bring 0, 1, 0, right? No, the 0 on the left is no good. You have to bring in the next 0. Okay? Remember, if that's a 0 on the left, it's no good. You must have 3 bits that the left part must not be a 0. Now, 100. Divide by that again, bring down 101. And who's next? Yeah, go on.
0.
1 0, is it? 0. 0 1, is it?
0.
0 1. That's it. And we get rid of the zeros on the left, and we continue. That's it. There's no more. What we have is less than the length of the generator. Then we finish. We stop. And that's called the remainder. We call this the remainder. And that's going to be the part. The other good thing in binary you have a 0 or a 1. The 1, whatever you get here, is the remainder is also the complement. So you don't have to work out. Remember the example earlier on, we divided 37 by 5. The result is 7. 7 times 5, 2. The remainder is 2. We needed to work out what's the complement of 2 to 5, which is 3. Here, that remainder is also complement. So that's it. Once you finish doing that, then that's exactly what needs to go with as a remainder. But remember, it's important. You must send 2 bits. Now you need to fill zeros on the left if you have to. Right? If whatever bits we put here, that's the length of the CRC that we need to send. So in this case, we have to send 2 bits. The one on the right is 1, so the other one is 0. And that's now the data we are sending is 11011001, and that follows. If the 01 is not really part of the data, that's what they call CRC. They call it CRC. Or they in some networks they call it, this is the frame check sequence, FCS. But many people, they just call it the CRC. That's what's the CRC complement that you need to send, that the receiver will use. Now, this new number, if received by the receiver as it is, and if it's divided by 101, it will give it a perfect division with no remainder. That's the general idea. This is like earlier on, when we worked out the 37, we added 3 to it, so it's 40. So if the receiver gets 40 here, then divided by 5, the remainder will be 0. So now, I just write the 4th step here. These are the steps you need to follow if you are a sender. So first you identify the generator, the data. You append a few zeros. These are the number of zeros that will be appended. Divide all this by the generator. And now whatever remainder you get, append it to the original data. And that's your frame gone. So that's if you were a sender. Now I'm going to show you how the receiver works very quickly, and we go over it next time. So this is what the receiver got this is a receiver sent us, the sender sent us this frame, and you know the generator is 101. This is an agreed number. Now, what do you do as a receiver? First, identify your generator, your data, and your CRC, or frame check sequence. So where's the data? Where does the data end here? Yeah. Appends it to the data there. See, this is your data, and the remainder is 1 or 01. That's the one. It's appended to the data. This is the data, and that's the actual.
Yeah, that's the checksum. But what about the?
No, that's not checksum. That's the actual remainder that got from here.
So that's the remainder. But like 101.
No, that's automatically known. If you join the network, they tell you this is the generator. You have to include it part of the setup of your network. Okay, so you already have that. Everybody has that who wishes to communicate. Now the next thing is to append zeros. Do append zeros? No, this is the only difference. Do not append zeros. Normally, I shouldn't even say it, but I find many students, when I say, you are a receiver, you receive this data, and they first thing they append zeros. Don't append zeros. They're already appended. That part, you should know now, this is your generator. You should know where the data is. Once you know the generator is 3, that means the extra information, the CRC, is 3 minus 1, which is the last 2 bits. If this was 13, then the last 12 bits are CRC, not part of the data. If everything is perfect, that's the one you throw away. The rest of it is user data, right? If everything is good. Now, let's divide this by this. Start the division. So, I'm going to go through it quick. Same XOR operation. You just bring the first 3 bits. 1, 0, 1, 0. If I make a mistake, please remind me, right? And then bring in 1 bit, 1, 0, 1, and this is a 0, 0, 1. And make sure you follow me. So it's 1, 0, right? I intentionally sometimes make these mistakes, and sometimes make them into. Okay, the next one is 101, and that brings us 0, 0, 0. Then we have to bring this 0, that's no good at all. And then the last one is 1, 0, 1. Now, that one, remember the 1, 0, 1 just goes at every, it went down at every location here. Now, at the last location, 1, 0, 1, and 0, 0, 0. And now, the remainder equals 0. So there should be no. So the last thing, if remainder is not equal to 0, if you get any number here at the end, that means there is an error in your data, in your frame. It means error, throw away the frame. If the remainder equals 0, what does that mean? Yeah, so it means, generally it means there is no error. But because there is a tiny little possibility that there might be an error and you still get a 0, very, very unlikely, but it's possible, then we say most likely, don't say there's no error. Then you'd be partly correct, but not 100% correct. Most likely, no error. If it's 0, and in this case it's a 0. Then now you have to do the last thing as a receiver. Get rid of the CRC and just give me the user data, the frame without the extra part. So this is the only data. That's 1, 1, 0, 1, 1, 0, 1. That's the user data. That's the frame received without error. If this bit here, the remainder, what remains with the receiver is not 0, you throw away everything. You say, okay, this frame contains an error. We don't know which part, we don't know which bit, but it contains an error. And this is the fastest, this is the most used, the most efficient error detection system in use today in probably 99% of the networks around the world. The CRC error detection system. This division of, it's not division, It's actually, it goes through the bytes of the frame as the frame is being transmitted. And whatever is left, it leaves it in memory, it goes with the frame. So it's really fast. You don't even have to do the full operation first and then send the frame. No, you can start with the first few bytes and you tell the sender start sending while you're still checking. And by the time you finish checking, the transmitter is almost finished to catch up with you. You leave the remainder in there until you go. So it's the fastest way. First, all the operations are logical, and the other thing, you don't have to wait and sending until you finish CRC. No, you can send while you're doing the check. And also, it has a very low redundancy. It has a very high rate of error detection, and it's extremely fast. So far, this is the best error detection system and the most used in the world. Next time, there are 2 more error detection systems we'll do next lecture. Thank you very much, guys. I'm sorry for keeping you.